Yeah, where I'm saying this one most important. Not pipe flow. It's not really power law fluid actually. Okay, it's more general fluid. Okay, but later we do apply it to power law fluid. All right. So basically, yesterday I showed you that we could measure the viscosity using those viscometers. All right, the different types of viscometer. But another way of measuring viscosity, or in this case, or if you want, if you have non-Newtonian fluid going in a pipe and you want to predict, normally what you want to predict? Yeah, no, you want to predict. Normally you want to predict the pressure drop, all right, or relate the pressure drop to the flow rate, all right. So, basically, this is similar to the energy equation, except we drop all the terms. We just have the pressure and the losses. All right. So that's all. Because there's nothing else. Height the same, velocity same, in out, everything same. Fully developed for the pipe. So this one normally all that is left. All right, is the head loss. Okay, head loss is equal to delta P on rho G is equal to head loss is equal to something. Okay. All right. So we normally that's where we start. Okay. First of all, I did this earlier, but where? I did this earlier in a pipe. Yes, a pipe. Okay, so you have P and you have P here. P say P1, P2. All right. So in a steady flow, I can say the sum of the forces, the X, is equal to 0. All right. So P1 times the area, pi R squared. R can be any distance actually, R. All right. Can be any distance. R can be anything from cannot be more than less than 0. The subscript I, this one that the notes here use, because they follow from the textbook, from the book, and the book that covering this section use the subscript I. I means inner diameter. Oh, sorry, inner. R means inner radius. Later on you see a DI. DI means inner diameter, which is the diameter of the pipe. All right. Okay. So pressure minus P2 pi R squared minus shear stress times the area is 2 pi R times L equals to 0. Okay, now. All right. This pressure times area minus this pressure times area minus the shear stress on the side of that dotted line. All right. Shear stress times the area 2 pi R, the diameter, times the length. That's the area on the dotted side. That's equal to 0. So first thing, we can cancel the pi. We can cancel out 1R. All right. So you get P1 minus P2 multiplied by R is equal to shear stress over 2L. Okay. Or P1 minus P2 over L is equal to shear stress over 2R. All right, which is equal to shear stress. So if you take this all the way out to the wall, you can take over to Ri. Okay, the same. Or we can take that shear stress di over 4. Okay, or or shear stress at the wall. This is the wall already. Subscript W means at the wall is equal to di delta P over 4L. Okay, So this relationship very important. If we if we can measure delta P, we can know what the shear stress is at the wall already, or at any other location. Alright, but normally we do at the wall. Alright? So if you're doing this type of experiment, it's quite easy to measure delta P. Alright? And okay, so if you can measure delta P, you can measure the wall, get the shear stress and back and forth. Okay. Alright, is that okay so far? Then the other one, the Newtonian fluid profile for Newtonian. Alright, we did earlier. Alright, the profile is U is equal to, I think, U max 1 minus R on Ri squared. Okay, it's a parabolic profile. Alright, from earlier pipe flow, from earlier. Okay, which is also equal to 2 U mean. Alright, if you want to prove this part, we proved it earlier, it's in your notes. Okay, if you don't remember, you have to look back. I proved it. Alright, 2 U mean 1 minus R on Ri squared. Okay, so the du on dr is equal to 1 no. So 4 U mean R on Ri squared minus. Is that okay? Yes, so far. So this is the UDR of this one. Right, Ri is a fixed, so that doesn't change. So U with respect to R. Okay. So R squared becomes 4R over Ri squared. Alright? Yeah, U max is 2 U mean. Yeah. Okay, so this is the mean velocity, this is the maximum velocity. Alright. So du on dr at the wall is equal to minus 4 U mean Ri over Ri squared. So this one and this one can cancel, is minus 4 U mean over Ri. And it's also actually R, if I in terms of D, is equal to 8 U mean over D I. There's a minus. Okay? So this number, because we don't know what the velocity gradient at the wall for our funny fluid is, so we use this as the characteristic. Alright, this is like a guess. Okay, so normally we call this 8 U mean over Di is flow characteristic. Okay, so that is a, because we do, later we'll work out what the velocity gradient at the wall is for non-Newtonian flow, for the general flow, general fluid. But for Newtonian fluid, we know that the velocity gradient for laminar, okay, I forgot. Laminar velocity gradient, laminar flow velocity gradient at wall is this one. Okay, earlier laminar. Okay, so and in our pipe flow experiment, I said we can measure delta P, easy. Okay, you also measured it before. I said I don't know with the Lotus one, some got problem, but we measure delta P, no problem. We can work out what the shear stress at the wall is. All right, we can measure the flow rate, so we can get this one. All right, you know the flow rate, then you get flow rate divide by the area, you get the mean velocity. All right, so these two we know. Okay, so what we to help our make our life easier, we say this one. This is our model. K prime 8U over Di to the n prime. Okay, this is our model. model and definition of K prime and N prime. Alright? So, for pipe flow, we can measure the shear stress on the wall because we measure pressure drop. We can measure AU over DI because we measure the U is me, because we can measure flow rate quite easily. So, what we do, we just assume that it behaves like this for any particular situation, and we can plot that. So, how we plot that? Well, we take log of both sides. Take log shear stress on the wall equals to log K prime plus N prime log 8U over DI. Is that alright? MOCI, if I log, the log rule is if it's multiply, you can plus. If it's to the power, you can bring down outside here. Okay? So, this one we can measure, this one we can measure, and we plot. Okay? We do an experiment. This one is, the bottom one is log 8U over DI. Normally they take ln. So put ln. Yep. That's the definition. It's just, they are just numbers at the moment. Alright? So, we just assume that for a particular instant in time, the flow behaves like that. Okay? K prime and N prime may not be constant. Alright? They may be constant if you're lucky in certain cases, but they may not be constant. In other words, if I plot log versus log, ln of this one, okay, I may not get a straight line. I may get like that. Okay? If I get a straight line, fantastic. Then this one means K prime and N prime equals constant. Alright? Most likely in that case it's a power law fluid. Alright? Equals constant implies power law fluid. But in general, it may not be constant. So, alright. So in general, you could get another line that looks like this. This is called case 1. Case 2. So at any instant in time, at any point, let's say at this particular point, we can map out the gradient and extrapolate here. Then that's the value of N prime is the gradient, K prime is here, the value. Alright? So we can get this graph by plotting. So in other words, we can measure K prime and N prime by plotting this graph. And if it's a straight line, very easy line. Just take the gradient, it's N prime, the intersect is K prime. But if it's not a straight line, if it's a funny curve, then at any instant, any point, any particular flow rate or whatever, any flow rate, you can always work out what the K prime and N prime. Alright? So for at any instant, you can work out any, when I mean instant, any particular situation, you can work out K prime and N prime. But in that case, let's say you increase the flow rate by 50%, the K prime and N prime will be different. Alright? So the K prime and N prime is just what do you call it? A curve fit for our pipe flow experiment. Alright? So this relationship we dream up. Okay? Alright, this K prime and N prime we dreamed it up. We just say, okay, let's fit that one, and then we plot that one. Alright? So in other words, the K prime and N prime can be measured through the pipe flow experiment. Is that okay so far? Alright. Okay, so this part is any questions so far? So remember, yesterday we talked about K and N for the power law fluid. That is only applied to the power law fluid. Alright? K prime, N prime is a curve fit. So they are different. K prime is not K, N prime, well actually N prime is N, but alright, but in general, K prime and N prime is curve fit. Measured from for any fluid flowing in a pipe. Alright, yesterday one K and M is for power law fluid. Law, fluid, model. It's only a model. Alright, we can't tell the fluid to behave like that if it doesn't want to behave. Alright? Is that okay so far? Alright, so here on it gets a bit complicated. Are you okay so far? Alright? So that's the easy part. Okay, I've mentioned this one, I mentioned this one. Hopefully D delta P over 4L, correct. Mentioned this one. Alright. If you so far we can do the experiment, can measure K prime and prime, but if you want to know a little bit more about what's going on, if you want to know about the velocity gradient, that's the shear rate at the wall. Alright? The shear rate at the wall, that's we need to know the velocity gradient, or the shear rate at the wall. We need to know the strain rate at the wall. And the strain rate at the wall we don't know. The strain rate at the wall for Newtonian fluid we know is AQ over DI. That's the characteristic that we chose. Alright? But in general that could be any it's not likely to be AQ over DI. It's non-Newtonian. Alright? And there's a new apparent here. Alright? If we knew the velocity profile, we will know the alright? But we do not know the velocity profile except for the Newtonian flow and laminar flow we know the velocity profile. So big problem. Alright? And okay, so we know for velocity for the Newtonian fluid, that's the velocity profile. Okay, it came from the notes earlier. Alright. Okay. So this part, I just mentioned briefly. If you want to go through the maths yourself, you can. This part is a bit painful. Alright. So this part tries to work out the velocity profile, not velocity, the velocity gradient at the wall, the strain rate at the wall, as a function of the other parameters and so on. Alright, as a function of K prime and N prime basically. Because you can measure K prime and N prime. Now we want to estimate the velocity gradient, we want to estimate this one. Don't know. Alright? So what we do is we take the flow rate, alright, is equal to the integral of the velocity times area. Alright? Then we integration by parts. Okay, then you get like this. This one actually quite hard to follow, so I just mentioned it. If you want to do it yourself, you can, and then you want to discuss with me, you can. But normally this part, not so examinable. Because it's quite complicated. Okay? I think maths also, it came out one of those books. Okay. I try to think about any easier way to do it, but I can't. Okay? So integration by parts, you realize the first one is 0. So the flow rate is this integral, which is this integral. This is the velocity, the strain rate, and as a function of radius. Okay? And then we know the shear stress is a function of net pressure, the shear stress at the wall. Okay? So we can relate the shear stress at any radius is that one, that's top equation here. I got no pointers, so I use here. Alright, shear stress at the wall is this one. So you can get the ratio of shear stress is just the ratio of radius. So R is this one. So the dr can be this one. These ones are constant. And then this one you replace here. Instead of dr, you replace with this one. And then you arrange. And then you again rearrange in terms of flow characteristics. So we want 8u over di is 4q over this one and that one. And after that, more integration, more rearranging, blah blah blah. Alright, there's no magic here, it's actually all just maths. Alright, and you come out with this relationship here. Alright, the shear stress at the wall. Okay, it's all up to you, you want to do it yourself, by all means, please go ahead. But basically, the shear stress at the wall is equal to the shear stress at the wall for Newtonian fluid multiplied by this thing. This is a correction factor. Actually, this d log, AQ over di over d log, shear stress, that's the gradient, isn't it? This is actually 1 over n prime. Alright? That's all. Okay? So, what we get from here is basically this relationship here. Alright? After a lot of running around, okay, we get this relationship which we need, which that's the only one we use actually, but if you want to work out how the shear stress at the wall, the strain rate at the wall is equal to the strain rate at the wall for Newtonian fluid, and this one is equal to 8u over di multiplied by, well, this one. Okay, 3 over 4 plus 1 over 4. 3 over 4 plus 1 over 4 n prime. Okay? Because here, d ln shear stress on the wall divided by d ln 8u over di, that's the gradient, isn't it, of this curve, is equal to n prime. Alright? But that one I had it the other way around, that's why it's 1 over n prime. And therefore this one, you can also write 3 plus 3n prime plus 1 over 4n prime. Alright, it's just factoring it. Okay? So, we can, I repeat, from earlier we can measure k prime n prime. Alright? And we know k prime n prime. And we know 8u over di. Alright? And here is just an n prime. We can actually know what the strain rate at the wall is. Alright? And we also know what the shear stress of the wall is. Alright? Shear stress of the wall, what is it? Delta P di over 4L. Alright? So we know this one, so then the mu apparent, I think there's a P, equals to shear stress on the wall over this one. So at any instant, based on our measurement and a bit of analysis, we already know what the viscosity is at that. Alright? At that instant in time, what the viscosity at the wall is. Here. Given that this particular shear rate and this particular strain rate. Alright? So, now what we have done, we have converted our pipe flow experiment into a rheometer. Okay? Cheaper. Rheometer expensive, of course, tens of thousands of ringgit. Need to buy expensive calibration fluid and so on and so forth. With this one, as long as we can pump that Newtonian, that funny fluid, whatever it is, into a pipe, we can measure k prime and n prime. Alright? We can measure shear stress on the wall. And once we know n prime and the mean flow velocity, we can also work out the apparent viscosity for any given shear stress or strain rate. Alright? So as we vary the flow rates, alright, we should be able to get a plot. Something like this. What was it? Shear stress versus this one, dot at the wall. We can get our plot. We have made a viscometer or stroke rheometer. Fantastic, right? Save tens of thousands of ringgit. Yeah? No, there's no power level. This one is equal. This one, they are equal. This is the velocity gradient at the wall for Newtonian fluid. This is the velocity gradient at the wall, or the strain rate at the wall. This one is equal to du over dr. At the wall means at the wall. R equals to Ri. Alright? The strain rate at the wall. Okay? Is that okay? Any questions? Alright? So the only complicated part is getting this one here. That's the difficult part of this whole thing. The other things all look quite easier. Okay? I said, if you want to follow this maths, it's not impossible. It's maybe a bit challenging. but can be followed. Actually, if you done maths A, or you haven't done maths A, you done integration by parts and all that, isn't it? Differentiation and so on. So follow this one. Okay. All right. So I've mentioned all this one already. Okay. Turns out by no, I'll skip this part, but I don't want to talk this one. Confusing. Okay. So sorry, my mistake. This one is new apparent. Okay, sorry. This one here, I better not write this one AP. AP is actually a different one. This one is mu A. Okay. All right. So normally the next thing is when we start our experiment, all right, we may not know all this already. Okay. So we define a new creature called mu AP, which is all right, which is what is it? Shear stress on the wall over 8U over di. All right. This one is so the mu apparent is the apparent viscosity, the real one. This one is just a guesstimate, a guess. All right. So we don't know what the shear stress on the wall is before we do the experiment. So we need to guess, and a good guess would be just use the flow characteristics instead. All right. So with that, we can come up with the Reynolds number. Rho U D. Sometimes in this chapter they use di, so that's the pipe diameter, inner pipe diameter, over mu AP. Okay. And what else? Okay. So this one is just the velocity grade, may not be known at the start. Okay. All right. And if you put mu AP inside there, and we put this definition inside there, okay, so if you put these two together, you get this one. So you should replace the shear stress on the wall with K prime, 8U over di to N prime, you get this one, and you put this one into the Reynolds number, you get this funny thing. Alright? Okay? Don't worry, you don't need to memorize this one. Alright? Normally all you need to do is remember the Reynolds number is that one and mu AP is that one. You should be able to work out the rest here. Alright? But this is just the RE prime one. Okay, and the reason why you need RE prime is because, okay, here changes a little bit, so I better talk. So all right, given K prime and N prime, so normally the problem will give you can do the measurements, get out the K prime, N prime. All right, predict pressure drop in pipe. Okay, so some fellows they're smart. They say, okay, and every year I get this fellow saying, okay, shear stress on the wall is K prime 8U over di to the N prime. All right. So predict pressure drop for given flow rate. So they give you the flow rate. So they give you Q. From Q you can work out U. From U you can put inside here given K prime, N prime, D, everything. You can work out the shear stress on the wall. All right. Equals whatever. Is that so far okay? And shear stress on the wall equals to delta P. What's the relationship again? Di over 4L. Then therefore delta P equals what? Easy what? And that's correct or not? Alright? Is that correct or not? Too easy. Oh, question like over 10 marks. Oh, anyone, huh? Something's going on here. Okay. This is correct. Alright, correct. If laminar flow. Alright, but not all cases the non-Newtonian flow will be laminar. Sometimes it's a bit in the transition in the turbulent range. Normally, non-Newtonian fluids are very viscous. So don't expect the Reynolds number to be 10,000 or 100,000 or 1 million. But the Reynolds number could be 5,000, could be 4,000. Alright, so it could be slightly into the turbulent range. Alright, then in this case, then you, for any given problem, don't just jump straight away like this, although it looks very easy and you can do it. Alright, you must also check if it's laminar, then yes, this is correct already. Alright, so that's the definition. Alright, but if it's not laminar, then how to check? You need to work out. Alright, correct approach is we work out Re prime. Alright, Re prime equals what? Alright, that's from the earlier. Rho U D over mu AP. Mu AP is equal to shear stress or shear stress on the wall over 8U over di, which is equal to K prime 8U over di to the n prime, because you do not know the shear stress on the wall yet. N prime over 8U over di. So this one you can find a number, you can put inside here, you can find this one. Is that okay? So step 1, you find your Reynolds number, Re prime. Alright, step 2, you look up this graph here. So this if assuming, this one is assuming laminar flow, this one is correct, but you need to check. Correct approach, step 1, find Re prime. Step 2, alright, look up graph, look up F. I haven't tell you what that is, but I'm going to tell you now. F fanning. Okay, so there's this graph here you're supposed to look at. This is like the Moody chart for non-Newtonian flow. Okay, so laminar region, you don't need to look up the graph actually. Same. It's the same as if you did, I showed you earlier. But in the turbulent region, anything above 2000, then it's dependent on n prime. N prime 0.2, 3, 4, 5. So depending on your Re prime and your n prime, then you look up and you get a number. This one, also problem. This one here is called the fanning friction factor. Alright? Up till now, just to confuse you, up till now we were using the Darcy friction factor. Alright? So, the difference is F fanning is defined as the shear stress on the wall over half rho U squared. Alright? Whereas the laminar flow, Newtonian flow, we use the head loss is equal to F L on D V squared on 2G, that one. This F is Darcy. So this one is fanning. Okay, that's because the reason why we have two is because this chapter was taught by mechanical engineers. This chapter was taught by chemical engineers. Alright, so just confuse you there. Actually, both conventions are correct. Alright, there are two conventions around. Alright, this is the fanning friction factor, that's the Darcy friction factor. So the Newtonian flow, pipe flow, all those, Moody chart, etc. use this one. Okay? Moody chart, use this one. Okay, and this week in our tutorial we'll still use this one, because this week we're doing pumps and Newtonian flow. Next week, the tutorial when you do non-Newtonian flow, use that one. Okay? And actually you can show can show. I think I won't show now because I think time running out. Can show. I think F fanning is F Darcy. I think this one over 4. It's over 4. Okay. That's why this one, if you see the laminar range here, is 16 over Re prime. No. Before here. Alright. So in laminar range, F fanning is 16 over Re prime. F Darcy equals to 64 over Re. Alright. So to be the same, 4F fanning equals to F Darcy. Alright. So this is just to show the relationship. But normally, what your procedure you would do, all right? And I'll do a example on Thursday. All right, because I think I don't have time now. All right. Basically, all right. Basically, once you found look up the F fanning, you can work out. I complete the step 3. Step 3, we can work out the shear stress on the wall is what? Right, because from this relationship. And step 4, delta P is equal to shear stress on the wall equal to delta P on L D on 4. And therefore, delta P equals alright, that's the proper approach to solve. So the typical problem, they give you K prime and N prime, and then ask you to, and the flow rate, ask you to find the pressure drop. But last year, exam, they even twist this around, maybe iterate. They give you K prime and prime and then the pressure drop, ask you to find the flow rate. So that one you need to guess the flow rate and see what the pressure drop is, and then, alright? Okay, which we'll do, if you don't do next week, we'll do some time for the maybe in the revision. Okay. Any questions? Yeah. Yeah. Normally K prime and prime. If you have to do the experiment, then you can find it. But normally in the problem, they will give you the K prime and prime. Wait outside for a minute.